minute. 5. The talk is 25 plus 5.
25 plus 5. Okay. Thank you. Thanks, Arun. I hope I'm audible. I'd like to thank the organizers for inviting me for this nice conference. So this is Mike. Yeah. Okay. So firstly, a big thank you to the organizers for inviting me to this first in-person meeting after this long pandemic. It's really great to attend a meeting in person. So without further ado, let's begin. So I'll be talking about simulating young magnetized jets from supermassive black holes, and trying to understand the different facets of simulations that we can perform in this modern age, and what they can tell us about these jets and how they interact and affect the environment around them. Of course, this is not a work alone done by me alone. This involves a large collaboration from various international partners, both from the theoretical side as well as from the observational side. And I'll try to give you a bit snippets of the different kinds of results that we have nowadays. All right. So when we talk about relativistic jets from supermassive black holes, we are immediately reminded of these nice, beautiful images from the radio. And jets come in different forms of shapes and sizes. Large scale FR2 jets, FR1 jets, and of course, I wanted to highlight these two new sort of categories that are coming out, FR0s, blob-like structures, which are more compact, 3 kiloparsecs, or even these hybrid structures, which are FR2 on one side and FR1 on the other side, nicely called HIMOS by Jeremy Harwood and others who have been working on the LOFAR surveys. But jets are also an important driver of galaxy evolution. So jets, I hope this is the lecture, yes. Jets provide the galaxy as a very nice means of transporting their energy from the central nuclear region of the galaxy to its large extragalactic scales. The good thing is jets are very powerful, so they can really efficiently dump a lot of energy, potentially dump a lot of energy, and really energize the extragalactic environment and the environment around galaxies, and thus, of course, affecting how the galaxies grow and evolve. But the bad thing about jets, as often is quoted, is they are often seen in radio as thin collimated structures. So that really casts some doubt about the efficiency of how efficiently can the jets transfer or transport their energy or heat up the external environment. But as we know, that energy or deposition of energy from the central black hole to the large-scale environment is a key ingredient in galaxy evolution. Otherwise, we cannot get these mass functions correct. And of course, when you talk about AGNs, I'm talking about both jets and winds and any sort of outflow that the central black hole can give out to the system. And in this broad picture, what we are interested in to understand is what are the role of jets and how do jets affect this kind of systems? Okay, so some of the main fundamental questions that we are interested in is, do radio jets affect the host? Because of course, as I was talking about these large scale and beautiful images of radio galaxies, before they grow to such large scales, they do have to pass through the galaxy. So if the galaxy has some gas content within it, does the jet affect the gas within the galaxy itself? Or how efficiently, or how importantly can it affect the gas in the central regions? And of course, a standard argument against sort of not considering jets, and that traditionally has been, well, radio loud AGNs are quite small in number if you look at surveys. But that picture is also changing slowly. So usually, previously, it was always quoted as 10% of AGNs have jets. But that was mostly because the surveys were limited by their sensitivity. If you try to start lowering the sensitivity and thresholds, you find more and more galaxies are radio loud at the nuclear zones, as nicely shown by this result in Sabator et al. From the LOFAR surveys in 2019. So if you go lower and lower in the radio thresholds, you can actually have jets which are 100 and galaxies which are 100%. All of the galaxies are radio loud in some sense. So radio loud galaxies are more ubiquitous than we had previously thought, and it's important to understand how they can affect the galaxy. And one of the fundamental questions that always plagues us in the community of galaxy formation is, how is star formation rate actually regulated in the host? So in terms of the AGN feedback, we often hear that, okay, the AGN throws out matter, and that's how that depletes the galaxy of its star forming fluid. But are there other mechanisms? Does the matter always have to leave the galaxy? Can the central AGN regulate the star formation without even throwing out the matter? So that is more of a turbulence-driven regulation of star formation, and that's again something that we're interested in understand. And of course, none of this makes sense if we don't have any observational signatures that we can predict from this work and try to compare with the observed results. And I just wanted to highlight this particular picture because often it's always considered that radio jets may not really affect star formation, but that is not always true. This nice result from Nicole Nesvadova in 2010, which shows this main sequence lines. This is a Kennigan-Schmidt plot, so slightly different scales on the y-axis and x-axis. This is standard Kennigan-Schmidt of star-forming galaxies, and all these red dots, red triangles, are radio loud AGNs, where the star formation rate is lower by several decks. So in this particular systems, the AGN jet is probably affecting the star formation in some way. How and into what efficiency, that is still to be uncovered. So to understand some of these, we've been carrying out a series of simulations using the Pluto code. These are relativistic hydrodynamic simulations, and also magnetic fields were also included in the later phase. I hope I'll be able to cover that. And so by relativistic simulations, I'm not talking about GR. These are special relativistic flows, and we are launching the jets far away from the central black hole. So we don't need to cater to GR effects, but these are relativistic flows because jets are powerful relativistic objects, and that is what we take into account. So this is the first thing. So this is quite a busy plot. This is a mid-plane slice through a 3D simulation, and I'll show you a jet that's coming out of this turbulent distribution of gases. Filamentary structures are turbulent gas distribution that we've set as an initial condition of the simulation. There are two simulations. On the left-hand side, there's a more powerful jet of 10 power 45 ergs per second. On the right-hand side, 10 power 44 ergs per second. They're two identical ISM. But for now, let's just focus on one of these cases. So the top, there is density, and the bottom, there is temperature. All right, with this, let's see what happens. So initially, as you can see, the jet, if you did not have all these turbulent structures, the jet would have just gone through. But since you have some clouds resisting the path of the jet is finding it difficult. As you can just focus on the more powerful jet here, it is getting deflected and it's pushing the clouds around. It's almost like you trying to make your way through a crowded train station. You have to navigate through the different spaces and gaps that you find. And that's what is happening here. And as you can see in the temperature plot, there are some cold clouds getting trapped in the giant energy bubble, in a hot energy bubble that's being inflated by the jet. So all these cold clouds will have shocks that is penetrating slowly inside them. And these shocks will first of all, heat up the gas and also induce turbulence. So that has very important impacts on the nature of the star formation rate. Do focus on the right-hand side image now. You can see that this is a low power jet. The power is an order of magnitude lower. It is finding it really difficult to break out compared to the left-hand side image, but it does break out at a later point. So what's happening here is that even though it's a lower power jet, it is struggling, it is pushing the matter all around, but it is still a relativistic jet that is pumping out relativistic plasma. All this relativistic plasma is still shocking a large fraction of the galaxy. So it can still transfer a good amount of energy to the central nuclear region of the ISM. And all of this will have important consequences of how much the jet can affect the central regions of the galaxy. So although it's a low power jet by one order of magnitude, it is not to be discounted. That's the message. So this was a jet that we're going through. Okay, the slide transition. Okay, now it has happened. So that was a jet that is going through almost like a spherically distributed turbulent distribution of gas. What about disks? Now, if the jet is vertical, you might be prone to thinking that, okay, the jet just goes out of the disk. It doesn't affect how things are happening.
Is it an isothermal atmosphere? And what is the...
Yeah, I didn't talk about the details of the technical stuff too much, but what we have is a two-phase or a multi-phase media with
what about the Mach number? What's involved?
The Mach number of the jets.
Yeah,
we have that relativistic jets inside this spine of the jet. We have Mach numbers of 10 plus, but again, these are relativistic Mach numbers.
So you have a two-phase.
I have a two-phase, an external low density atmosphere, which is like a radial profile standard atmospheric solutions, and then I have a dense distribution of gas. So as I was saying, you might be prone to thinking, okay, the jets are vertical, they just escape out of the galaxy, don't affect the gas too much, but that is not true. Even so, what I'm showing here is 3 simulations where the jets are inclined at different angles to the disk plane. Again, these are slices of a 3D simulation. I hope you can see my arrows here. Yes. So even look at the left-hand side image. Although the jet is quickly escaping out, these contours are contours of gamma of 2. So these are the relativistic part of the jet. It is still, creating a large-scale bubble that is engulfing the entire nuclear disk of a few kiloparsec and then compressing it. It is even launching small scale outflows. You can see these clouds being moved out. So even if it is a completely vertical jet, there is less coupling. It still affects the disk to a large scale. But of course, if you incline the jet, and there is no reason why the large scale jet has to be perpendicular to the disk. So, the central angular momentum of how the matter is increasing at the black hole, that's at a completely different scale compared to the large scale disk. So, and it's been shown in Cepheid galaxies that this orientation is completely random. And if you incline the jet, you have a jet passing through more of this medium. And that's why it is, launching this clouds and comet-like structures, and it can really affect the gas distribution. So one of the key things that we want to study next is how do the jets affect the star formation rate? So these simulations are fine, but in previously, all someone would do is just take a given density above a threshold and then compute the star formation rate based on the density alone. But as we know, the star formation rate has a lot of other factors that are folded into it. For example, the turbulence, the magnetic fields, which we are not considering for this kind of work. And this work is being led by my PhD student, Ankush Mandal. He has a poster outside. So if you're more interested, I'll encourage you to look at Ankush's poster. What I've done is we've identified these clumps or clouds that we have in our simulation. So this is a picture from Ankush, where he's identified some clouds here. And then once we identify the clouds, we can then perform some statistics and identify the turbulence inside these clouds, and then apply a subgrid physics to compute the star formation rate. So this is very well established in the domain of star formation, pioneering work done by Mark Krumholz and Christoph Federer, and routinely done in that community. What we've done is taken that theory and applied it to large scale simulations as a subgrid physics. So what we find is the velocity dispersion of these clouds do increase by almost an order of magnitude from the initial value. And if you increase the velocity dispersion, you also start increasing this quantity called alpha virial, which is a measure of the kinetic energy to the gravitational potential energy. So kinetic energy being high means you're sort of resisting the collapse due to the gravitational potential energy. And this can lead to a decrease in star formation. Just wanted to highlight this, that you just need to increase the velocity dispersion by a factor of few here. I just plotted it here. You can see more in my review article in 2021. If you increase the velocity dispersion by a modest factor of few, you can reduce the star formation rate by almost an order of magnitude. So it doesn't really take much to reduce the star formation. So impact of the jets or any such outflows on star formation rate due to a turbulence-driven phenomena can be possible, and it doesn't take much to do it. So what we find in this particular case is what I'm plotting here on the right-hand side plot is the star formation rate surface density. I'm sorry, the label got cut off, I see, and the density on the x-axis. So if you look at the blue circle, so all the gray dots are cases for the clouds without getting affected by the jet. So these are no jet or control simulation. And the colored dots are from the clouds that have been affected by the jet. So if you just look at the blue circle firstly, all these clouds have slightly decreased in star formation rate compared to the gray dots. So this is a case of a negative feedback. But you have this outlying clouds here. They're mostly clouds in the central region of the within 1 kiloparsec. Their star formation rate surface density has increased substantially. So this is a case of positive feedback. So what the jet is doing is, in the central region where it is directly impacting the clouds, is compressing the density. There it can enhance the star formation slightly. But on the outer reaches, it can reduce the star formation. So you can have both negative and positive feedback happening in a similar system at the same time. And such systems have also been seen in observations. I'm not going to the details of that. Now, star formation is fine. How do we connect with observations? Again, this is one aspect that's being led by my another PhD student, Meenakshi. She also has a poster outside. I encourage you to look at her poster as well if you're interested. What we're trying to understand is what are the signatures of this jet ISM interaction and how can we identify them from observations? And this will help us and enable us to directly point out or locate regions where jets are interacting with the gas distribution. So for example, in one of these cases, what we're trying to do is finding the regions that are shocked by the jet and trying to estimate the shocked emission. But what we're after is not the total luminosity of the shocked emission, because that is, of course, limited by the resolution. But what we are interested in is in the kinematics of the shocked gas, because that is what we can ascertain with some certainty from this kind of simulations. So this is one particular case that I'm showing here, where the jet is slightly inclined to the disk. And this is the shocked O3 emission. You can see the entire disk is starting to glow because the gas is getting shocked all through. So this is an integrated image of surface brightness. And these are line profiles that Meenakshi has created, and then taking the widths of the lines to create the parametric measure, which is W80 width, which is the 80% percentile of the lines. And as you can see, the interesting result, I'm just highlighting one of the interesting results here. The jet is inclined to the disk, but the highest line widths are at regions perpendicular to the jet. So we have high dispersion at the tip of the jet as well, but there are high dispersions perpendicular to the jet. What's happening here is, although the jet is getting obstructed by the dense gas distribution, then the plasma loses its relativistic flow, and all it wants to seek out is the path of least resistance. And the path of least resistance is the vertical regions, which is the minor axis of the disk. So there are outflows being created here. As you can see, some cometary clouds being pushed out both in the top and bottom, and that's what's creating these flows. And this has actually been observed recently by Giacomo Venturi in this particular case, where the jet is actually highly inclined to the disk in IC5063. And you have enhanced O3 dispersion to both perpendicular and both in the direction perpendicular to the jet. And also another case I'll highlight. So, but what is important here is to understand this: we would not have been able to understand this had we not had spatially resolved information about this jet asim interaction. And these are Muse simulation, so that enables us to have high spatial resolution. And this is important to understand this. So these are some of the line profiles that Meenakshi found in this particular case.
You have 10 minutes.
Thanks. So I'll just go through some of the observation results. So there are many different examples of jet asim interaction. This is not a comprehensive overview. I'll just highlight some of the results that's been coming out from our group, led by some of the observing partners that have, for which we have been providing some simulation backup. This particular case led by one of our PhD students in Australia, Henry Zavaro, we find that although the jet is 100 parsec, we have an extended shocked H2 region that's about a 2 kiloparsec in region. So you can understand the scales. The radio jet is 100 parsecs, a few hundred parsecs. The extended shocked H2 region is 2 kiloparsec. What it means is we have a lot of missing flux. Once the jet sort of goes and hits the clouds, become really diffuse, it's really difficult to get out the radio emission from the extended regions, but the jet can still affect the gas distribution. Another example, again, very nice Muse observations by Aishwarya Giridhar and Chris Harrison's group, is again a particular galaxy where the jet is inclined. And this was multi-phase observation, both the ionized gas as well as O3 with ALMA. You can again see the high velocity dispersions in O3 perpendicular to the jet. So again, it goes to show that we need spatial resolved information to understand this kind of physics that's happening. Another nice case by Nicole Neswadba. This is a jet asim interaction in a spiral galaxy. Large-scale jets in spiral galaxies are really rare, but this was first found by Joydeep Bagchi in 2014, and then Nicole followed it up with Muse. Now we have Muse, that this is ALMA observations. You can see that there's enhanced dispersion at the rim. And from our simulations, we show that indeed if the jet is coming out of the system, it can create patches of enhanced dispersion at the inner regions of the jet asim interaction. Another nice result from Nicole, she found this particular galaxy, which is supposed to have positive feedback. Usually it's thought that, okay, this is the radio contour, and these are the star formation regions in black. So it's really nicely aligned along with the jet. So it's always thought that positive feedback will only happen resulting in increase in star formation. What Nicole's find is that's not really the case. The star formation efficiency is not that high. Again, this is points to nicely some of the work that Ankush has found, that although the stars can be promoted or induced to form, the efficiency may not be higher because you are also inducing turbulence. Now, of course, this nice result that we had earlier this year in Nature Astronomy from Raffaele Morganti's group, and I'll talk about more of it in the next slide, where we found in a particular system that the jet is actively clearing out about 75% of the cold gas mass in the central few kiloparsec. And this again nicely, this was we provided some observational backup to with our simulations. But we showed that really this is one of the first unambiguous detections of radio jet affecting the gas. So the AGN is low luminosity, it cannot drive this wind. So jet asim interaction has a lot of different aspects. And in the last remaining few minutes of my talk, I just want to introduce some of the new methods we are trying to implement to study further the jets. Now, what I'm talking about so far is how the jets are interacting with the multi-phase gas distribution. What I have not really talked about is a synchrotron emission, for which the jets have been famous for. And this is again something that we're trying to understand, but our focus has been in trying to understand how we can infer some physics about the shock acceleration, where it takes place, how it's affected, and how it can affect the synchrotron emission. What we've done here is now produce a hybrid new scheme where we put in particles along with the fluid. And we launched lots and lots of particles. Our final simulations had about tens of millions of particles. And each of these particles represent a non-thermal electron distribution with the power law, as that would be giving our synchrotron. We have different mechanisms to account for the energy losses due to synchrotron, as well as diffusive shock acceleration at shocks. So the particles can travel through this fluid. It can get reaccelerated at these recoil-efficient shocks, but there's also turbulence that causes internal shocks in the cocoon, and there can be reacceleration in those cases, and all of this we can infer. So this is one of the results of this, and again, 3D simulation, you're seeing a slice. On the left-hand side is just a jet evolving and the density cut. On the right-hand side, I'm overplotting the particles, and I'm in color, I'm plotting the maximum Lorentz factor of the particle distribution. You can see, as is expected, the particles have this island-like, the jets have these island-like structures because that's where the shocks are, internal recoil emission sites. It goes to the top and then flows back in a thing. But what's interesting is if we can now see if we have internal turbulence inside these jet cocoons, these particles can take very weird and wild trajectories. For example, look at this particle. It's going up to the jet, making a loop, coming back inside the jet and going up. And this is because there's local Kelvin-Helmholtz vortices that are making the particles in go-round groups. So since this is a session on magnetized cases, I've been talking mostly of hydrodynamic simulations. I wanted to introduce this with a magnetized case. One of the results that we can produce from here is comparing, say, two jets of different magnetic fields. On the left-hand side, more magnetic field, so the jet remains more collimated and there's more magnetic pressure support in the central region. The right-hand side jet has a less magnetic field. So sigma is a ratio of the magnetic field energy to the Poynting flux to the jet enthalpy, and the relativistic enthalpy. So it's not a direct measure of the magnetic field, but anyway, it has lower magnetic field. As you can see, with lower magnetic field, it's more prone to Kelvin-Helmholtz instability. So the magnetic field distribution really becomes very patchy. Another nice example that we have is this kink instability. So this is a 3D instability. I can only show the 2D movies for now, but I have shown a 3D image on the bottom right corner. You can see as the jet is moving, it is trying to tilt and bend. And this is because this is a very highly toroidal magnetic field that is making the jet, and that is instigating this instability. It's called the kink modes that makes the jet bend. And the synchrotron image of this thing, as using the particles that I had mentioned, you can see the tip of the jet is producing a hotspot at different locations at different times. For example, till now it was a nice, well-behaved jet. Now it will slightly go towards the right, as I'll just spend 1 minute on this slide. It will slightly go towards the right because now the kink mode has started to develop. So it will point here and then it will start pointing here. So essentially, when you see an integrated image, it will be very difficult to discern where the exact hotspot is, because the hotspot is shocking all the gas around it. And that is also inducing internal turbulence in the cocoon. One interesting find from this particular set of work is, if you have such cases where there are imaged instabilities that are churning the gas inside the cocoon, you can have internal shocks. So particles will get accelerated not at just the top of the jet, but also inside the cocoon. And that has strong implications of synchrotron cooling and how you use the standard formulae for inferring the ages of the jets. And I'll finish in a couple of slides. In this context, what we're trying to say is, how can we infer, how does this affect the radio spectrum? So what I've done here is I've plotted the particle spectrum at different locations of the jet. This is, and I'm plotting one of the cases at different frequencies. So I'm all synchrotron. 1.4 gigahertz, this is K band in synchrotron and X-ray in synchrotron. In the standard radio band, you can see just a standard hotspot with some polarization vectors here aligned along the jet. But as you filter out the less energetic plasma, you start getting into the shocks. And you can see that in the X-ray synchrotron image, for example, you have clear identification of a top hotspot and some internal shocks because of this turbulence inside. And what's interesting, and this is probably my last slide, is we have now a way of understanding that particles inside these turbulent cocoons can be accelerated to a different energy. So essentially you have a two population system. One population that gets accelerated at the top of the jet, then a standard cooling down with a broken power law kind of phenomena as we have for cooling electrons. But the other where they re-accelerate at shocks. So this is secondary electrons. And this has been theorized in one of these papers in 2015 by Eileen Meyer, where they found that this observed synchrotron nicely fits this curve, but this X-ray flux does not fit other mechanisms like inverse Compton interaction with the CMB. And they promoted a second synchrotron with a question mark. And now we can see from the simulations that this is indeed viable. If I plot that the previous simulation that I showed, this new plot, it is turning over, but then it's turning back up again with higher flux at this higher frequencies. And again, more such cases have been found by Giulia Migliori. I'll refer to you to this paper. So summarizing, I'm out of time for this. Jets. So I've talked about two different kinds of way of looking at jet, but this kind of simulations give us a holistic picture of how jets affect the central gas distribution and what are the different kind of physics we can infer. And for this, we really need to do different kinds of simulations for this. So just to summarize, jets can potentially strongly couple with the host galaxy's gas distribution if it has gas. And it has been a standard case that it's always quoted that radio galaxies are gas poor, but that is not completely true. As I showed, there are several examples of gas-rich radio galaxies. Hybrid modeling of both non-thermal electron population as well as fluids are required to understand the physics of what is happening to these particles as they're accelerated and producing emission. And MHD instabilities can strongly affect the dynamics and the emission mechanisms. And I hope in future we'll have more and more spatial resolved observations as well as spatial resolved simulations to help uncover this kind of systems. Thank you.
You finished on dot. So first I'll ask the audience to ask the questions, and then we will go to the online questions. Very good talk.
Thanks.
What I was a little bit want to know is that in the galaxy and jet interaction simulations you did, the special relativistic code, right?
Yes.
Okay, so there is no way you could put the gravity because at the galactic disk that's self-gravitating.
Yeah. So we don't have self-gravity in these simulations, but we have a effective restoring force, let's say.
Okay.
As I was pointed out by Arun, we have this external atmosphere that has a radial distribution, so it's hydrostatic balance. So we have an external restoring force. It's not a true gravity, but we've checked that in a weak Newtonian limit, it comes down to the same equations that we use.
The other thing I want to know is that in your emission simulation, okay, so you are also generating a lot of
Yes.
I mean, for some.
Yes, for some.
Right? And you are creating all those structures.
Yes.
Right. Is there any way of measuring the turbulence?
Yeah, so measuring the turbulence is a very tricky thing to do in the small scale domains. For example, the power spectrum and things, because we don't have a periodic structure. One thing that we did was trying to find the correlation length of the magnetic fields. And that's there in our 2020 paper, which is based on. And we showed that for these cases where the instabilities pick up, magnetic fields are really patchy in small scales. That can be sort of give some indication of the turbulence, but we need to perform more statistics to infer that. Go into that.
Okay, Ajit.
Yeah, very good talk.
Thanks.
So what kind of computer resources do you need for the simulations? And typically, if you take a paper, how long do the simulations take?
Yeah, so for example, the first batch of simulations I showed with the jet ISM interaction, I'll give you a brief idea of the amount of resources I used. I ran this code on an Australian supercomputer system using around 3,000 cores. And they ran for several days. So our total computing budget was usually the yearly budget was in the range of 10 million CPU hours. 10 million is not used, but for the final production runs, we do need about 5 million CPU hours. For the later half, we need 5 million CPU hours. So yeah, we need millions of CPU hours in terms of standard resources.
It's very significant.
It's quite demanding, yes.
And with GPUs?
We are porting to GPUs right now.
Because with so many young people around,
yes,
you could increase the productivity by having many simulations going at the same time.
Yes. So regarding GPUs, we'll also be organizing a GPU workshop. I'll send out the email to ASI soon. But for this particular case, as I was saying, that exascale computing has really driven the European superclusters now. And that's why everybody is porting to GPUs, and we also are trying to catch up.
Okay, last question from the audience.
Oh, thank you. So thank you for your talk. Though I'm not from this field, but I was quite intrigued when you said that these jets are actually increasing the star formation. So I was wondering if you'd like to comment on what sort of stars you're talking of. Is it the generic, let's say, proton plus proton thing that we have for the sun, or it's just some other thing?
Well, I'll not even go into the details of the chemistry of that, because what we have is a molecular cloud, let's say, and the composition of the molecular cloud would be standard for any. So the star formation rate would be exactly standard. So it was not recording before. Okay, that's fine. So what's happening here is that molecular cloud is getting compressed, and that is what is causing this enhancement in star formation. In terms of the chemistry, it'll have the standard chemistry of the stars, but of course these are getting polluted by the metals that are being dredged up and being mixed with the molecular cloud, and such mixing simulations have not been done.
Sorry to interrupt. We just have one question.
Yes.
One question from the online.
Yes.
Maybe two. Slide 10. Slide 16, sorry, you showed that there were shocks in the jet. Were they caused because you had any variations in gamma, or did the shocks arise just from the interaction with the medium and turbulence?
The shocks,
this is from Arun.
Hi, Arun. The shocks just naturally appeared because of the way the fluids are interacting with the medium.
Okay.
Although they are relativistic simulations, but then it starts to decrease in the backflow, and that's where the shocks come.
Okay. If there is no jet activity from the central object, this is from Ramiz Akhtar, what are the possible reasons for star formation? And number two, what is the effect of negative feedback of AGN on SFR?
Well, negative feedback of AGN, of course, means there's a decline in SFR. So if there is no central activity, of course, the star formation will proceed in a normal way. And I'll not comment on that because that's a different kind of a thing on a star formation driven scenario. But I guess the question you really want to ask is how much of an effect it has on the galaxy's stellar population distribution. I would say for a single jet activity, not substantial. It will only slightly decrease the star formation. At least in our simulation, we find by a factor of few. But sustained jet activity over multiple episodes, it can add up.
Thank you very much, Dipanjan. We'll go to the next speaker, Pallavi Bhat.
Can you stop my screen share? My mic is frozen. Okay, it's fine. Stop.
Pallavi, I'll warn you at 15 minutes. You have 25 plus 5.
Yeah, thanks again to the organizers for inviting me to give this talk. And as Dipanjan said, I also share the same sentiments that this is actually my first in-person talk in like 2 years. So this is great. And if I look confused at some point, it's because this is new for a while now. Yeah, so let me get on with it. In the animation, basically what is being shown is the phenomena of reconnection. What's happening is that there are anti-parallel field lines coming together, and at the point of intersection, there's a current sheet, and since current density is curl of B, it's perpendicular to the plane. And what happens at the current sheet is that the magnetic fields interact, and there is strong resistivity, so the magnetic field lines break, and then they reconnect, and they move out of the reconnection site, and that's what's going on. So as you can see visually, there's a topological rearrangement of the magnetic field. And since there is resistivity involved, so this has got to have some dissipation. And there's also conversion to kinetic energy in the process. And there can be heat and also particle acceleration and so on. While this is a steady state model of reconnection, there are models which are also bursty and eruptive and violent and so on. Okay, so how can we use magnetic reconnection to understand astrophysical systems or some phenomena. Starting, you have space physics where you can have magnetospheric substorms. So what that is that you have solar wind coming in and interacting with the Earth's magnetic field. So I have a small movie which I want to show you. Okay, so there are these magnetic field lines sticking out of the sun, and then at some point they reconnect and gets thrown into the space, and that comes in and interacts with the Earth's magnetic field, and there is reconnection happening, and the field lines then drape over to the other side, and then again there is another set of reconnections that take place, and then the plasma all go and come towards the pole and interact with the atmosphere there and basically create this beautiful aurorae. So you can see that reconnection is actually playing a role in what you see, like beautiful stuff out there in space. And then, of course, in astrophysical plasmas, reconnection has been shown to be important for getting particle acceleration in pulsar winds and jets, and also is being used as a model to understand gamma ray bursts. And actually substantial literature of reconnection comes from laboratory research, because it is really important for magnetic confinement in fusion. And so there's lots of reconnection research which is coming from there. The early models in reconnection were basically steady state models like Sweet-Parker and Petschek. The Sweet-Parker model is a slow model, does not lead to like fast reconnection. And the Petschek model is typically not seen in simulations or experiments. So recently, in the past few decades, there has been like a paradigm shift in the magnetic reconnection research. There has been brought in what is known as plasma instability. I'll talk about it a bit more a bit later. So I want to first introduce the basic Sweet-Parker model to some of you who are not like familiar with this field. So the schematic is as it was before. So there is this current sheet in the middle, and there are anti-parallel magnetic field lines coming and interacting in the current sheet. And the current sheet itself has these dimensions. So 2 delta is the width and 2L is the length. So how can we derive a reconnection rate or something? So the way we go about it is, okay, from mass conservation arguments. So if there's a mass flux going in via the length, then it has to be equal to the flux that is coming out via the width. So that gives us the first constraint. So V in is the ingoing velocity of the flow, and V out is the outgoing velocity of the flow. So V in into L equals V out into delta. That is the first constraint. Second one comes from energy conservation arguments. So since there is a conversion of magnetic energy to kinetic energy, so the outgoing flow will be actually equal to alphanic velocity. And the third constraint comes from Ohm's law, which is basically relating the current density, which is induced by electric field and magnetic field charge carriers in the plasma. So inside the resistive layer, it can be simplified to just contain the resistive term, and outside the layer, you can ignore the resistivity. By having these two constraints, you can match them at the boundary, and that will give you the third constraint. So putting all of them together, you can get a reconnection, actually non-dimensional reconnection rate. So that is equal to the Lundquist number to the power of -12. And Lundquist number itself is like magnetic Reynolds number, except you will replace the characteristic velocity by the alpha velocity. Okay, so that was the Sweet-Parker model. One thing that I should mention is that if you look at this, it has this negative exponent power law, right? And that will lead to like really, really small values if you put large Lundquist numbers. And that is typically the case for all astrophysical plasmas, most astrophysical plasmas. So it doesn't help in explaining observations, right? So Now I come to the latest thing, the plasmoid instability. This was first formally derived by Lorero et al. In 2007. So the schematic remains the same. So now the inner current sheet is actually quite thin, very, very thin. And that is what is enabling this plasmoid instability to take place. There are the usual flows in antiparallel magnetic fields. So what happens is that this system becomes violently unstable to formation of magnetic islands called plasmoids. So you can see like a structure of magnetic island that's given by the isocontours of the magnetic flux over there. So these plasmoids form, and then it leads to like bursty reconnection activity. And if you do this derivation, then you can get your usual growth rate and the maximum the mode which is growing at the maximum growth rate and so on. And you can see that the power law exponents now are positive values, which means that if you have a really large Lundquist number, it's going to be violently like all the instability will grow violently. Okay, and the thing is that people did not see the plasmoid instability much earlier because the critical Lundquist number that is needed for this instability is very, very large. So it was only in like early 2000s people started seeing like these plasmoids and so on because they had the computational power that would enable them to see this. And turns out that if you go to the steady state of this instability, it becomes independent of the Lundquist number. So you don't have to bother about Lundquist number anymore. So here I'm showing some pictures of the plasmoids, both in magnetohydrodynamic simulations and also in PIC simulations, particle and cell simulations. So you can see that there are plasmoids of all sizes, which means that these plasmoids basically coalesce and form bigger plasmoids and so on. This is a nice model because this enables you to get like violent and bursty reconnection, which is important, which will be important to apply to astrophysical phenomena, which are violent and bursty and so on. So in that line, I want to like briefly tell you about the astrophysical applications. One example is on the left. It's by Sironi and Spitkowski, where they have tried to apply this plasmoid instability-driven reconnection to understand particle acceleration. So what we have done is to run these particle and cell codes solving the kinetic equations. They have been successful in basically obtaining particle acceleration to the order that you can get like really hard spectra. So by hard spectra, I mean that the particle spectra across the energy has an exponent which is either 2 or less than 2 and so on. And the other example is this one by Cherity et al. 2013, where they have tried to apply this to understand gamma ray flares, basically the synchrotron counterpart of the gamma ray flares from Crab Nebula. So observation showed that the synchrotron radiation is basically beyond the burn-off cutoff. And they wanted to understand this, and they again used PIC simulations to accelerate particles beyond the burn-off limit, as you can see from the plot here. And the very latest application that has come in for these plasmoid instability-driven reconnection is to understand black hole flares. This work is as recent as January 2022 by Bhat. So what they have done is to run GR-MHD simulations, and they show that quite close to the black hole, these current sheets form and lead to the formation of plasmoids, as they have shown in the inset. These current sheet forms in the inner magnetosphere quite close to like 2 to 3 Schwarzschild radius. And they are able to, again, like get these black hole flares via the plasmoid instability driven reconnection. So general takeaway message is that you can use plasmoid instability driven reconnection. This is a fast reconnection to understand like any high energy phenomena. So there are these papers coming out recently on fast radio bursts, gamma ray bursts, and so on. All right, so at this point, there is a question that what is the interconnection or the interplay between reconnection and turbulence? Because most of the astrophysical systems are turbulent in nature. So while that is the larger question, already in 1999, Lazare and Vishniak came up with a model in which they include turbulence. So it's called the turbulent reconnection model. Here they model the wandering of the field lines too, and then put in that aspect into their estimate for the reconnection rate. So that leads to fast reconnection rate. However, like a lot of people who want like violent bursty phenomena are not really necessarily happy with this model. Okay. So in this context, the next story that I want to present is one of the recent study that we did, that is to explore the role of reconnection in decaying MHD turbulence. In particular, it's non-helical MHD turbulence that I'm going to talk about. So what is non-helical? For that, I have to first tell you what is helicity. So magnetic helicity is this topological quantity. It gives you a measure of the links, rights, twists, kinks, etc. in the magnetic field. So mathematically, it is given as the volume integral of the vector potential dot product with the magnetic field. So the interesting thing about this quantity is that it is very well conserved in astrophysical system, because astrophysical systems have a really large magnetic Reynolds number. So in that limit, the magnetic helicity quantity is very well conserved. So that property leads to this particular interesting thing that if you have turbulent plasma and it has magnetic fields which are helical, then that turbulent plasma depicts inverse cascade. So as you can see in the plot, there is the spectrum of magnetic energy which is shifting to the left, and that is showing you that there is increase of magnetic energy at low wave numbers. That means larger scales. So this is an interesting thing, that if you have magnetic helicity in your system, that leads to growth of magnetic energy at large scales. So now that I have told you about this, it should come as a surprise if there is inverse energy transfer, even if there is no helicity. And this is what these people saw in their simulations, Brandenburg et al. In 2015 and Zurich in 2014. So they ran this really huge simulations. So you can't see this phenomena at like lower values of Reynolds numbers. So it seems that if you are at large enough Reynolds numbers, then you can have this inverse transfer. So again, you can see the magnetic energy spectrum, which is shifting to the left. And what is being done in these simulations is that, there is this periodic box in which they are solving the MHD equations. And initially, all the power is being put at really large K values or very small scales. And the system is allowed to evolve, which means it kind of freely decays. The initial velocity is actually equal to 0, and then it comes up and then it also decays. So as you can see, the kinetic energy shown in these dotted lines are subdominant to the magnetic energy. Okay, and the two things that I want you to note is that this phenomena shows two scalings. One in spectra, that is k to the -2, and since the magnetic energy decays, it goes down as t to the -1. So this I want you to keep in mind. And you can see that if you pull out a slice of the magnetic field out of the simulation domain, there is this feature of inverse transfer, which is shown in how the structures are growing over a period of time. So even though they look like they are at the same strength, but actually by the last slide, by the last panel, it has decreased in strength. So in 2017, Muni Ju was running. She was looking at this particular problem of 2D island merger. So what she has done is to. I mean, I'm going into this because there's a connection that I'm going to make with this problem and the other problem, because the overarching question is, even though there is no helicity in the system, how are we getting this inverse transfer, right? So in this system, what she has shown is that there are these initial condition has these checkerboard magnetic islands. Each magnetic island corresponds to a current filament. So when you introduce perturbation to the system, it goes unstable, and the islands which are of the same color, they interact with each other, they come together and they coalesce, they form larger islands and so on. And this goes on, so you get larger and larger islands as time goes. So this is quite similar to the picture that you saw previously, right? And this is interesting. So what's happening is that the islands are able to merge because there is magnetic reconnection that is facilitating this merger. And so actually magnetic reconnection is responsible for the inverse transfer that you see over here. So what we did is to actually take again a random initial condition instead of that laminar thing, and see if the same dynamics pan out, and that is indeed true as seen from these plots, in the sense that there is inverse transfer that happens. I want to show a small movie which shows this whole activity. So you can see that because of the randomness, there is some flow which is being generated, turbulent flow, and then that pushes the fields around, so such that they can coalesce. And at the intersection of any of these two combining, there is current sheet which is forming, and that leads to reconnection and so on. So we know that this is true in the 2D case. The question is whether reconnection is responsible for the inverse transfer in the 3D case as well. Also the interesting thing is that if you look at the scalings, temporal and spatial scalings, that actually matches with what you get in the 3D case. And so you have this t to the -1 and k to the -2, which is absolutely coincident with the 3D case. So this makes further the case for the fact that perhaps reconnection is at the core of, the inverse transfer that you see in 3D. So we did run the 3D case, and again you can see if I pull out a slice, then it shows these very similar kind of structures. But then note that these structures are not as symmetric as that it was in the 2D case. They are a bit more elongated. And if you see it on the 3D box as well, you get this picture. But of course, these elongations are randomly aligned. They are not in any specific direction. And that tells you that there must be like local anisotropy, which is causing these elongations. So perhaps the 2D like dynamics persist in 3D. So the thing that helped us to nail this whole thing is this plot. So what I have shown is the way the BRMS, the RMS value of the magnetic field is evolving with time. So on the left, we have these curves from 2D simulations with different Lundquist numbers. So if I were to divide the time axis by the reconnection time scale, then these curves actually collapse on top of each other, as you can see here. And that tells us that the reconnection time scale is actually the dynamical time scale. And we did the same, we played the same game in 3D. And of course, the collapse is not as great. But if you notice, as you increase the Lundquist number, the curves get closer to each other and the gap decreases. So this is telling us that the diffusion effects which are which are there in lower Lundquist number simulations actually reduce as you increase the Lundquist number. So you need higher Lundquist number simulations to show that this is indeed the case. So with this, I hope I have convinced you that the reconnection has a strong role to play in decaying turbulence, and perhaps also in other cases. Recently, we are looking at also the helical case as well, because actually, if you want to understand physically how things are going on in the helical emission turbulence as well, perhaps reconnection has a role to play there as well. So this is like a short movie from the simulation that Shreya Dwivedi, the student who is working with me, she has run. And yeah, I hope this comes within the 1 minute that I'm supposed to have. Otherwise, anyway, so basically we are in the process of investigating this as well. And with that, I will just summarize. So plasmoid instability is this fast reconnection that is applicable to understanding bursty high energy astrophysical phenomena. And also reconnection is something that we think is responsible for the inverse energy transfer in decaying turbulence. And basically the takeaway point is the decay timescales are governed by reconnection timescales. And also we think that perhaps reconnection has a role to play in helical energy turbulence as well. Okay, thank you.
Thank you, Pallavi. Audience questions? Yes.
Hi Pallavi, I'm Kamlesh. First of all, thanks for such a nice presentation explaining all the aspects of reconnection in astrophysical plasma. I have two things to say actually. First one is information and second one is question. And the information is, if you go to your first slide where you said that PET-check reconnection is not seen in the simulations, I think that is not correct, because there is a paper by Betty, Terry Forbes and Priest that shows the PET-check reconnection in the presence of uniform resistivity all over the domain. And when we start with PET-check reconnection, then, and if we let it evolve, I mean they let it evolve, then it leads to ultimately the sweet Parker reconnection. So there are a number of papers, I mean few papers, but those are less. Yeah, but the second thing is correct, that PET-check reconnection is not observed in any experiment or observation. And my second one is the question, and that is regarding the bursty high energy astrophysical phenomena. So do you mean bursty by impulsive nature of the explosive phenomena, or is it something different?
Well, okay, the first comment that you made, yeah, so okay, the thing that I wanted to impress upon is that basically it's not as ubiquitous, or it is not naturally occurring. One can kind of create simulations, of course, but it is not naturally, more naturally occurring is a sweet Parker.
Yeah, that I agree.
Okay.
Yeah.
And the second thing is, yeah, so this is slightly different. So here, basically the bursty nature comes from the plasmoids that arise in the current sheet. So these plasmoids that come up, they coalesce and then they leave the current sheet and so on. So it leads to bursts. But the impulsive thing could also have another feature associated with it, which is like, if there is accumulation of energy over a period of time and there is some kind of trigger which leads to reconnection. And that is something that is still under research, and that's, yeah.
Yeah, actually I'm confused between the impulsive and bursty, because both are similar. And by impulsive, what is impulsive for me is the energy released within a period of very short time scale, and the development of currents and electric field within that range.
Right.
If it's going to be a long answer, we'll move it because there are
okay, we
questions.
can talk later.
Thank you, Pallavi, for a very nice talk. I was just referring that in solar context, we are also seeing plasmoids, their size distributions in a streamer belt driven by some reconnections. In fact, the work was done by the photographer who is busy in taking the picture. But my question is, the size distribution, we also saw some power law distribution and all that. And we were only referring to Bhattacharya's earlier work. Is there some more work recently available in terms of this, distribution of the sizes from the plasmoids?
So actually, there are a few papers recently, like 2018-19, where they have looked at the kind of sizes that you get in these plasmoid simulations, like what is the distribution function and so on. So yes, there is some work in that. And I'm not quite sure now what the I think it was a peak distribution, but I'll have to check on that.
We can discuss it later.
Okay, I'll take an online question. This is from Dipanjan Nandi. In planetary magnetotails, we often see plasmoid ejections mediated by a reconnection. Do you believe this may have a role to play in planetary mass losses when the process is very efficient, or for example, when the stellar magnetic field is very strong?
Hi, Divyanu. So, yeah, nice question. I think there will be mass losses because actually these plasmoids are dense structures, but I'm not sure how efficient they are. And as such, I am not sure if there is work that's being done in this domain. But yeah, this is something that I would also like to know. Yeah.
I'll close with my own question.
Okay.
Now, in your simulations, you had this, contours, I think flux contours. I don't seem to see that. I'm sorry. Yeah, okay. I don't seem to see how it's geometrically affected, right? I mean, in the sense that if you doesn't seem to show O-type reconnection, for example, and the way you've shown the flux contours, O-type reconnection should be possible. Isn't that? Is it a?
I mean, this is like a 2D.
Correct. 2D thing.
Yeah.
So how would you?
I mean, actually, the reconnection that is taking place is Sweet-Parker reconnection. Yeah, because the time scales that we have used to understand the reconnection dynamics is coming from the Sweet-Parker calculation.
My point is that isn't it a little restrictive in a sense that if you have a turbulent magnetic field, there are other possible ways in which.
Yeah, so the 3D
from
thing
a geometric
is,
sense, yeah.
Yeah, so the 3D thing is open. It's not clear like what is happening. But the conjecture is that because there is some anisotropy at small scales, it could be similar to 2D kind of thing. But of course, it will have its extra calculations. Yeah.
Thank you very much. In the interest of time, we'll move ahead. And the next talk is online. Maheswar Gopinathan.
Yes, sir. You can share your screen now.
Maheswar, can you hear me?
Yes, I can hear.
You can start immediately.
I hope I am audible and my screen is visible.
Yes, please.
Yeah. Okay, let me thank the organizers and the SOC for giving me an opportunity to present some of the work that myself and my team have been doing. And this work is basically, I'll show some of the results that has been obtained by some of the PhD students who have been working on this field. So we know that star formation is one of the most important process in astrophysics, basically because it gives us an idea of how galaxy formation takes place and how the galaxy is evolved. And the question is how the atomic intercloud medium, which has a density of about, say, 1 particle per centimeter cube, gets accumulated to form a typical molecular cloud and subsequently goes to form stars. We now know that Milky Way contains about 10⁻⁴ stars. These are of different ages and are at different evolutionary stages. Therefore, star formation must have been happening throughout the history of the Milky Way. We now are certain that star formation occurs in molecular clouds. where the total mass of the molecular portion in our Milky Way is about 10⁹ solar mass, basically coming from the various CO surface. Star formation is occurring towards the center of Milky Way. It even happens towards the edges and around our sun. And star formation seems to have happening in isolated and clustered mode. Here I show the Barnard 68, which is a kidney-shaped cloud. It gives a notion of a patch in the sky. This is one example of a star-less core where star formation is not happening in this molecular cloud. Now, Herbig-Haro 47 is an example where a single star is forming inside a small molecular cloud. And the formation is the presence of young stellar object is basically manifested by this nice outflow that is emanating from this source. Star formation seems to be predominantly happening in cluster mode, where enormous number of low mass stars are being formed along with massive stars. And if you look at a face-on galaxy like NGC 3147, you see these blue emitting regions. These are basically the star-forming regions which are distributed over the face of the galaxy. A typical molecular cloud is basically consists of phase 2, but then these are observed through molecules like CO. And the typical, the parameters of these clouds are like the temperature of 10 to 100 Kelvin and a density of 1,000 atoms per cc. Now, again, if you look at the Barnard 68 in various wavelengths, you will see that it is a dark patch when you look at it in a blue wavelength, but when you go to near infrared, for example, 2.2 micron, you see that the cloud is invisible, basically saying that the light from the background stars could easily penetrate through the cloud and reach us. This tells us that this molecular clouds are made up of dust grains, which extinguishes the light that comes from behind in optical and allows it to pass through. These dust grains emit in some millimeter and millimeter wavelengths, and the same Barnard 68 is seen like this when you look at through 250 or 350 micron. It also emits in molecular line observations. So what it tells you is that the molecular clouds are made up of dust and gas, and the various regions of the molecular clouds can be studied by multi-wavelength observations. There are several star-forming regions that have been identified in our galaxy. And when Herschel looked at these star-forming regions, what it observed was the omnipresence of long filamentary structures in ISM. There is an apparent tight connection between the filaments and the dense cores where star formation happens. Filaments are present even in diffuse non-star forming complex, such as the Polaris, which is shown here. And the Polaris is a translucent cloud. That means it is in the formation of getting into molecular. So this suggests that formation of filaments precede the star formation in the cold ISM. And any model that explains how star formation happens has to take into account the formation of filaments right at the initial stages when the molecular cloud is in making. Now, what is seen is that a main filament surrounded by a population of faint subfilaments or what is called striations. Here is an example of a cloud called Musca, where you can see there is a filament, a main filament, which is being connected by several striations. And the morphology of these subfilaments and the striations suggest that there is some sort of accretion is happening, which is feeding the material to the main filament. And these filaments are found to have a characteristic width of about 0.1 parsec. If we consider a competition between the self-gravity and the internal pressure, one can derive the minimum mass about which a cloud or a part of cloud collapses under gravity. It's basically the Jeans mass. It depends on the temperature and the density. And the time required for an astronomical object to collapse under its gravity is the free fall time, which is again depends on the density. If you assume 100% star formation efficiency and the free fall collapse, the global star formation rate is predicted to be about 300 solar mass per year. But actually, what is found in the galaxy is about 1 solar mass per year. That means that the clouds are not just collapsing at a free fall time, but it gets delayed. And the agents which are invoked basically to halt the collapse of these molecular clouds so rapidly is the rotation, magnetic field, and turbulence. Observations of the line widths seen in these molecular clouds show that there are non-thermal component apart from the thermal width, which basically is attributed to the presence of the turbulence. In 1949, it was when the discovery of large-scale magnetic field embedded ISM was made. They inferred the presence of magnetic field through polarization of starlight. In fact, the study was done basically to look at the polarization of the stars, but eventually they found that it is not one star, but the stars which are in a big region is showing similar high polarization. The polarization was found to be correlated with the extinction of the starlight as well, which gives an indication that the polarization is basically due to the same agent which extincts the starlight. Now, the polarization is caused when the dust grains are aligned with their minor axis parallel to the magnetic field. If a large population of the dust grains do that, dust grains which are asymmetric in nature do that, a starlight which passes through these dust grains, unpolarized starlight passes through the dust grains, get polarized with their polarization angle giving the sense of magnetic field. The same dust grains which are aligned with the magnetic field can also give out thermal radiation, and the thermal radiation is also found to be polarized. There is an offset of 90 degrees between what you see in optical and what you see in the thermal radiation, basically what you see in sub-millimeter or millimeter wavelengths. If you look at the polarization map of Milky Way, here the length of these lines are connected to the degree of polarization, and the orientation is basically from the north. If you look at this, the high polarized magnetic or the polarized vectors are parallel to the galactic plane, giving you a sense of the orientation of magnetic field in the galaxy. The Planck has given the sub-millimeter polarization map of the entire galaxy, of course with a low resolution. But what this tells you is that again the polarization is parallel to the galactic plane, and there are presence of loops which you can see even in the optical polarization measurements. Now here you require multi-wavelength observations to infer the magnetic fields of a molecular cloud, basically because through the periphery of the clouds you could see the stars in the optical wavelengths. So here here is a cartoon which I show how this is done. So the optical polarization, the starlight can pass through the low density outer regions of the cloud. But if you see the inner regions, these are blocked by the presence of the dust grains, because of which you cannot infer the inside magnetic field through polarization. In that case, you need to go to near infrared. But the very high density parts of the clouds cannot be the magnetic fields cannot be inferred through the infrared region as well. For that, you need to go to the sub-millimeter wavelengths. So by combining optical, near infrared, which is basically the extinction of the starlight, and the sub-millimeter, which is basically the polarization measurement from the emission, one could map the magnetic field of the entire molecular region. There are several polarimeters available which can do this in multi wavelength. It's not a complete list, but I have just shown some of them. There are some polarimeters which are in India as well, and the results which I am showing is basically come from the Aries import and the IUCA IFOS, which had a small polarimetric element, and of course we used Planck, JCMT, and ALMA as well. The field of view of the import is 8 arc-minute, whereas IUCAA with IFOS combination is 2 arc-minute. So you need to basically, to map a magnetic field around the region, you need to really it takes a lot of telescope time to make a map of the entire region. There are certain metrics which are important in understanding the star formation. The one is the mass to flux ratio, which basically compares the magnetic totality. If this parameter is greater than 1, it indicates that the region is magnetically supercritical. That is, the magnetic field cannot prevent the gravitational collapse. But if it is less than 1, indicates the region is magnetically subcritical. That is, the magnetic fields can support the cloud and stop the collapse. The alpha Mach number, if it is less than 1, it is called subalfanic, indicates that magnetic fields direct gas motion. But if it is greater than 1, we say it's superalfanic, where it indicates the converse. The third parameter is the plasma decay. If this is less than 1, much less than 1, it is a magnetically dominant system. If it is much greater than 1, it indicates that a thermally dominant system. Now you can measure the magnetic field strength by considering that the fluctuations in the distribution of the polarization can give us what is the kind of the relative importance between the turbulence and the magnetic field. The Davis-Chandrasekhar Fermi method can be invoked basically to look at what is the magnetic field strength of a region based on the polarization measurements. Here, we can only infer the magnetic field strength in the plane of the sky by taking the dispersion of the polarization angles, indicating the distortion of the magnetic field by non-thermal gas motion. However, it is hard to tell whether a cloud is globally super or subcritical by direct measurements of these fields. It's basically because the conventional methods which measure the strength of the magnetic fields can give only one component. In the case of polarization, it can give only the plane of the sky component, whereas the Z-band observations can give the line of sight. And also there are significant uncertainties in the estimates, basically because of various parameters that come in, which are uncertain by itself. The one strategy which you can use is to tackle this problem is to see whether the cloud magnetic fields are ordered or oriented or random around a star forming region. Second, how the field lines are aligned with the structures like filaments, the minor and major axis of the cores, and the outflows that are coming out from the YSOs. This is a study which was carried out using combining the magnetic fields inferred from the optical data and the submillimeter data. So here the white lines are basically the mean inter-cloud magnetic field, and the red lines are basically the magnetic fields that are inferred towards the core region. And the idea here is to find out whether is it the core magnetic field is aligned with the inter-cloud medium. In this case, what we are inferring is whether the magnetic fields are mediated the formation of the cores also. Now this plot shows in x-axis it shows the magnetic field in the intercloud region is the orientation in the intercloud region, whereas the B core is the magnetic field in the core part of the cloud. In this study, 25 cores were used, which are within 2 kiloparsec of the sun. And what is found is there is a nice correlation between the B core.
I showed 9 minutes.
Yeah, B core and the ISM, which gives an idea that the core magnetic fields are basically correlated with the intercloud medium. Numerical simulations suggest that this is possible only if the turbulence is trans or subalfanic. There is a tight correlation seen between the Planck and the optical polarization maps. These lines are basically made from the optical, whereas the background fabric is basically inferred from the Planck. Now, if you look at these striations, as I mentioned earlier, this is shown here, and you can see that the magnetic fields are actually perpendicular to the nearly perpendicular to the filaments and parallel to the low density striations that you see. So this actually gives an indication that these striations are parallel to the magnetic field, and these are the feeding lines to the main filament in this cloud. Now, the molecular clouds are ionized. Basically, there is a degree of ionization, which is basically due to the cosmic rays. And if we take the ionization into account, this implies that uniform gravitational collapse will result in rapid growth of the field, preventing further collapse, basically because the flux is frozen into the medium. Now, if this is so, then what you would see is that if you take a spherical cloud and you try to collapse it through the magnetic field, then since the ions are coupled with the magnetic field and the neutrals are not, and when the neutrals move, they collide with the ions and they take the ions as well as the coupled magnetic field together. And what you would expect to see is some sort of an R-class morphology, and this has been seen in one of the cases where this is the first example of an R-class morphology in the magnetic field in a star-forming region. Now, there is, although the magnetic field may not be strong enough to prevent the formation of stars, it can have significant effect on the accretion. If we look at the limited case of flux freezing, then the cloud close to the fields close to the protostar become strong enough to break the rotation of the infall gas completely. This will prevent the formation of rotationally supported disk. Even if ambipolar diffusion takes away the magnetic field from the central core, the redistribution tends to trap it in a rings surrounding the star. Now, this can be salvaged if the magnetic braking, if the rotation axis of the cloud is not perfectly aligned with the magnetic field. Observations suggest that the circular discs, circumstellar discs typically are not well aligned with the parsec magnetic field. The results from a survey conducted on 16 sources show that magnetic field on a scale of 1000 AU, which is very close to the protostar, are not tightly aligned with the protostellar outflow. But there is a problem. The problem is that the outflows that are coming out of these YSOs could modify the magnetic field itself. Now, we looked at one of the classic cases of LDN 1157. It is a star which is a class 0 star, which is showing an outflow coming out of it. And what we have seen is indeed there is a mismatch between the magnetic fields and the outflow. But to mitigate the idea that the outflows which are coming from these young stars could modify the magnetic field, we looked at some of the sources which are really very low mass. And these have been identified by Spitzer in some of the earlier believed to be starless cores. Their internal luminosity is so low that their mechanical energy may not be sufficient enough to modify the magnetic field. In this study also, we found that there is indeed a difference in the, or there is an offset between the magnetic field and the outflow. And this is basically done using the optical polarization, which actually maps over the periphery of the clouds. To look at the interior magnetic field and the outflow, we did near infrared polarization using IRSF South African telescope, and what we see is indeed there is an offset seen in the outflow and the magnetic field at this close range. Now, this is another source, which is LDN 1521F. Here, what we have done is we use sublimeter as well to look at a scale which is 0.01 parsec, basically to see whether is the star formation, which is the magnetic field that very close to the protostar is aligned with the outflow or not. And indeed, in here as well, what we see is that there is a mismatch or offset between the outflow and the magnetic field. We tried to go down to smaller scales using ALMA, but we couldn't detect the polarization signals from it. Now, this cloud is in a highly complex region, which is suggested by the ALMA observations, where it shows arc-like structure, which could show that this is there is an accretion of material happening onto this core. It would be interesting to see what is the magnetic field structure in these supply chains. Now, if you consider that there are two filaments which are approaching, then they could collide and can form a central high density region, which actually gets into gravity can pull the material around it and then form a cluster mode of star formation. Here, because the material is being pulled by a high density region, the magnetic fields can modify. This is something called the hub filament structure, where there is a hub forming and there are several filaments feeding the material.
2 minutes.
Yeah. So we looked at one of the hub filament structure in one of the clouds in GC 7023, and this is the polarization map of the entire cloud made by the Aries polarimeter. So what it shows is that this cloud is forming a B-type star, and there are several structures surrounding it. We identified the filamentary structures which are around this cloud, and tried to see what is the correlation between the magnetic field and the structures that are seen around it. Towards the tail part of this cloud, we again identified a single filament around it, and we have seen the magnetic field and the filament, how they are correlated. And you can see that the magnetic fields are actually quite parallel to the filaments in this cloud. This is in a study where people have found what is the star formation rate in various clouds as a function of how their magnetic field is oriented as a function of the structure. For example, this is one of the cloud where it is parallel to the main filament, and this is an example where it is the main filament and the magnetic fields are parallel, and here the main filament is perpendicular with respect to the magnetic field. And what is seen is that the clouds where the magnetic fields are perpendicular to the filament, the star formation rate is quite low, suggesting that it is more efficient for the material to be transported along the magnetic field and goes into a region, something like hub region, where star formation can get enhanced. And for the cloud which I was showing, this indeed is the case. It has star formation rate per unit mass of about 2, which is, and the filament and magnetic field orientation is within 30 degrees. So, as summary, the polarization observations are a vital tool to map the magnetic field geometry of the molecular clouds. Studies show that magnetic fields are important, formation of the molecular clouds and subsequent star formation. More high-resolution observations are required to map the magnetic field, especially towards the close range of or close vicinity of the clouds and the young stellar objects. Could be that we could develop a near-infrared polarimeter in future for 3.6 meter dot. Yeah, I'll stop here. Thanks.
Thank you, Maheshwar. Questions from the audience? Okay, I'll move to the online section. There is no question in the online section. So I have a question, Maheshwar.
Yes.
So in one of the quantitative measures, your magnetic field, can you measure the magnetic field strength exactly in or roughly in the whole region, and how much of it satisfies the virial condition? Have you done that exercise?
Yes, you can measure the magnetic field towards the region basically by, there are several techniques. The popular one is using the magnetic, the dispersion in the polarization angle. And it is found to be about, say, of the order of 20 to 30 microgauss. And it increases with the density. So at very low density, it is not correlated with the magnetic field strengths, but at high density regions, yes, it is correlated with the density of the region that we are trying to probe.
Okay, there are two more questions. Okay, very good. Could you throw some light on the role of ohmic dissipation and ambipolar diffusion in reducing magnetic field strength on core scale? This is from Manash Samal.
Oh, for the ambipolar diffusion, yes, that is one of the the mechanisms that are invoked basically to remove the magnetic field from the core, because otherwise it is strong enough to resist the formation of the,
So the question is,
stars.
how
Yeah.
do you compare with ohmic dissipation as a ways of removing the field? So how do you compare?
For the ohmic dissipation, I've not looked at that with respect to the ambipolar diffusion. Yeah, that is a good point. Could be
There's
checked.
one more question from Maushmi Das. How common is the hourglass shape for molecular clouds? Can we say how important reconnection is?
Okay, so there are some studies where people are looking into the reconnection in the magnetic, in the star forming regions, but it's really difficult. So we can only say the magnetic field mapping. We don't know the polarity of it. The second is the hourglass morphology. Yes, it has been observed in a number of cases. For example, in L1157, which I showed, it shows an hourglass morphology. But we need to keep in mind that the things that we are inferring is basically a projected thing. So there can be a projection effect which could change the kind of geometry that we are looking into. So we need to know what is the real the space distribution of the cloud to infer that. But yes, there are observations which show hourglass morphology.
Thank you, Maheshwar, and thanks to all the speakers. Divya has an announcement to make before we break. Thank you.